So welcome. Today we're going to be talking about compositions of trigonometric functions. And I'd like you to consider if I had x squared and then I took the square root of it, what happens? They undo each other, don't they? Similarly, if I had root x and I squared it, it undoes it as well. Now, the challenge is you can't just take what's inside and clean them off. Or can you? Is that negative x or is that x? X. So we have to be careful to not just like cancel the signs. Sometimes we have to put a little thought into it, right? So what we're going to be talking about today is a composition of trigonometric functions. And we're going to start with this idea of functions and their inverses. You'll remember that if I take the function of an inverse, Fogg and Goff, remember that? You can check if something is a function by taking f of f to the negative 1 of x, the inverse. And what should you get to verify that they're inverses? X. Remember, it undoes all the stuff, leaving just x. Similarly, if I take the inverse of f of x, that should also undo it, bringing back to x. And so jump down here to number 1 for a second. If we're taking the ArcSine, inverse sine, of negative 1/3, and then we're signing that, what do you think we get? Negative 1/3. If we're taking the cosine of the ArcCosine of 2/5, what do you think we get? 2/5. Seems pretty easy so far, right? Let's jump down. Well, here. Let's go down to number 11. If we're taking the ArcSine of sine of 3/4. 3/4, I mean, sorry. What do you think? Well, it's screaming out to you that there's an issue here, isn't there? Good, excellent. So here's the problem. When we use ArcSine, we talked about last class that there's a limitation on the domain, right? We took the sine function and said, we can't use the whole sine function because it goes on forever. So what we had to do was pick a region that we wanted to play with so that we could get a chance to see all the possible y values. We chose that region. In other words, for the ArcSine, we put a limitation on the function that says its domain is pinched between negative pi/2 and pi/2. And as long as our answers fall in that domain, then the function does exactly what we expect. So problem number 7, if you take the ArcSine of sine of pi/4, is pi/4 within the appropriate domain of ArcSine? It is. Therefore, this one's just going to undo itself, and it's going to be pi/4. But if we come down here to this one, is 3pi/4 in a proper domain for us? No. It's not. So I have to actually draw it out and think about it. 3pi/4 is right there in our unit circle. We know that the sine of 3pi/4 would be √2/2. But now if we're asking ourselves, what's the ArcSine of √2/2, we know that we're not allowed to pick an answer that's in this quadrant. We can't use those quadrants. It's got to be from negative pi/2 up to pi/2. So where are we going to find √2/2 positive? Yep, quadrant 1. And so the answer to this is pi/4. So let's come back and look at cosine. If we take cosine of 5pi/6, is that going to put us into a realm that's okay, that we can just undo it because of the inverse cosine?
Yeah.
Do you remember the realm that we're allowed to have, the domain for cosine inverse?
0.
Good. 0 is less than or equal to x, which is less than or equal to pi. So although sine, we forced it to be quadrants 1 and 4, sort of, as 4 is, remember, the negatives. In cosine, we force it to be quadrants 1 and 2. What about tangent? It's the same as sine. Good. Just like with our even and odd properties, sine and tangent have something similar. Negative pi over 2 is less than, or, but not equal to, is it? It's just less than, because what happens at equals to? Good. It's an asymptote. So just less than x, which is less than pi over 2. We can't use those extreme values. Now, these are all angle measures, and here we don't even have angle measures. And so there's a difference here. In one case, we have the ArcTrig function on the inside and the regular trig function on the outside. And down here, we're seeing regular trig function on the inside and ArcTrig function on the outside. And these are two different processes. If I start with the inverse sine or ArcSine of x, what is x? Well, let me do it easier. Sine of x does what to x? It takes an angle, find the ratios. And then the ArcSine of those ratios tell us an angle. So of course, x ends up being an angle. But in this case, if we're taking the ArcSine of x, x has to be a ratio to start with. This little feature inside the parentheses makes an angle. And then we're saying if I take the angle and sine it, I'll get this ratio. So this is now the ratio for this one, which means x has to have what domain restrictions in order for this to work? It's a ratio of side lengths with sine. Excellent. -1 is less than or equal to x, which is less than or equal to 1. Because now we're looking at x as a ratio of the side lengths. In other words, the sine values, the y value of our function, and we see that it's got to be between -1 and 1. What about cosine? Same thing. What about tangent? Good. I'm going to actually just save myself a little bit of writing and use interval notation for that. But it's all real numbers, right? We can use any values for tangent because there's any y values in the original tangent function. Okay, so let's go through this. Come down here and tan, then inverse tan. Are we on the left side or the right side? We're on the left side. So then we ask, is what's inside here within my realm of acceptable domain? It is. Great. So I'm just going to pull it out. I'm going to let it undo itself. And did that satisfy here? When we had cosine on the outside, this value fell between -1 and 1, so we just pulled it out. What about this one? It's outside the domain. You guys agree? We've been saying that these values for sine and cosine have to be between -1 and 1. This is not. So we have to think about it. If I have this ratio of side lengths as a sine, what angle would that be? Is it possible for any angle, when I take the sine of it, to give me -7/6?
No.
Impossible. Does not exist. In other words, if the sine is the opposite over the hypotenuse, this suggests that in this triangle, the opposite side is longer than the hypotenuse. That's impossible. That just does not exist as an angle. But now let's move down here. What about inverse cosine of cosine 5π6? So I'd start by looking at my picture. Yeah, you can look up here and just decide. 5π6 is over here, right? And so what is the cosine of this value? I know the storm is distracting, but it's negative root 3 over 2, right? So now we're effectively looking at that. But then you'd end up looking back at your unit circle anyway, and you'd find this. Isn't this in the right region or the right domain for the inverse cosine function? So therefore, this will just come back out. It's 5 pi 6 again. They do undo each other. Take a look at number 12. I'm going to start by drawing it. This is what makes sense to me, rather than memorizing those domains up top. Tangent of pi. Tangent of pi is over here. And that's going to be the y over the x, so that's going to be 0, right? And really, it's 0 over negative 1, but okay. And now we're saying, what's the inverse tangent of 0? Can I just use the same angle again? Is this a valid location for tangent? No. So for arctangent, I need a value in here. What's the value in here that gives me a 0 ratio?
0.
0, good. Right, this one's a little tricky. Let's draw the picture. 11 pi sixths. I want to do the ArcSine. Is that where it's supposed to be? So what do I write as my answer? Good, Olivia. Or I would go whoever said that. Negative pi over 6, right? Yes, it's at the location of 11 pi over 6, but we have to match this domain restriction, choose the fourth quadrant to be like the negative 1th quadrant, so to speak. Negative 1/2 pi?
No, it's like, so like that on the side of.
Oh, you mean, could you do this and recognize that this is like then sine negative 1 of negative 1/2?
Yeah.
And then evaluate that? Yes, but when you evaluate this, won't you come back to looking at the unit circle anyway?
Oh, yeah.
So yes, you can do that, but I think you'll discover that there's a shortcut going right to the picture.
Okay.
There's 2 more twists on this. Flip to page 2, please. What do you notice about this one? It's not all sine and inverse sine, or cosine and inverse cosine. We're mixing the functions. But again, if we do this the same way, use our unit circle, pi over 6, the sine is equal to 1/2. And here I would do exactly what Caden just suggested. And now to evaluate the inverse cosine, the ArcCosine, which quadrant would I look for when it's a positive 1/2? Still quadrant 1, but it's a different triangle, right? It's got to be the tall triangle to give me the cosine of 1/2. So what's my answer here? Yep. Let's try 18. So start by looking at 5 pi sixths. What's the cosine of 5 pi sixths? Good. Now we want to find the arcsine of this angle. Excuse me, this ratio. Arcsine is where? Which quadrants? 1 and 4-ish. So negative root 3 over 2 is going to be an opposite side because it's SOHCAHTOA going down, negative root 3 over 2. It's going to have a 1/2 here for the x, but we don't really care about that. What's the angle value there? Negative pi over 3. If you've been limping along for your unit circle, you're going to find that's not enough. You need to know your unit circles. Okay, last piece of instruction. What's different about these? Not only is it switched, but are those on the unit circle? They're not. So again, work your way from the inside out. I'm doing inverse cosine. Does that have a restricted domain? It does. My answer is going to be forced to be in this quadrant. Since my ratio is positive 8 over positive 17, will I be in quadrant 1 or quadrant 2? Quadrant 1. So I'm going to draw some random triangle. I don't know what that triangle is. It's certainly not to scale. Call that theta. And if the cosine is 8 over 17, then I know that the adjacent side length is 8. The hypotenuse is 17. But in order to find tangent, I need to have opposite over adjacent. So I need this side. Pythagorean theorem, right? 8 squared plus question mark squared equals 17 squared. 64 plus question mark squared equals 289. Question mark squared equals 225. So question mark is positive or negative 15. Given this triangle where I've drawn it, what would I use? Positive or negative? Positive, it's going up. So question mark is equal to positive 15. In which case the tangent of this angle, I don't know what angle it is. Can I guess? It's somewhere above 45, but I don't know if it's 72 or 59. I have no idea. It doesn't matter. The tangent of that angle is opposite over adjacent. That's an 8. Okay, why don't you guys try this one yourselves now? Go. How'd we do? 5. Made perfect sense. I got it. I think I have the answer. 3. I'm not sure my answer. I got something. 1. I'm just going to wait till you show me. Okay, good. 3s through 5s. So I start off saying arctan has to exist where? 1 or 4, kind of 1 and negative 1, sort of. And if it's a negative value, does that belong up in quadrant 1 or down in quadrant 4? Down in 4. Arctan, tangent, TOA, opposite over adjacent. So that means this is negative 12 when this is 5. I'm always anchored at my origin point, my standard form of the angle. And to find my hypotenuse C, I'm going to do Pythagorean theorem. 5 squared plus negative 12 squared equals C squared. I can't tell you how many times I saw this on the recent test. What's the mistake they made? They kept the negative. And probably what they did is they said negative 12 squared. Okay, my calculator says negative 144. When they should have said negative 12 quantity squared. So careful of your calculator. It's not always better. So 169 equals C squared. So C is equal to plus or minus 13. Would we take the plus or the minus 13? Hypotenuse is always positive. Hypotenuse will always be positive. So now we've got this triangle. We want to take the sine of this. Sine is whatever what? Good. So sine of whatever angle this is, theta, is going to equal the opposite side over the hypotenuse we just found, negative 12/13. Okay, you have the period to finish off this packet, please, applying the composition of trigonometric functions.